All right, so this is going to be the first lecture for Chapter 5 of the lecture notes, Chapter 4 of the Bloomfield textbook, continuing to think about mechanical objects, right? And one of the things you might think is that as you go about the world, a lot of the machines and objects around us seem quite complicated, but in fact, a huge number of them behave according to the physical principles that we've already outlined in this class. Thinking about forces and accelerations, thinking about conservation laws, like the conservation of momentum, both linear and angular, thinking about the fact that energy is conserved, so it can neither be created nor destroyed, only shuffled between different objects or different forms within the same object. These basic principles are already enough to understand an enormous amount about the world around us. So we encountered a few of these things in Chapter 4 of these notes, talking about springs and bouncing balls and carousels. And in this chapter, we're going to talk about bicycles and rocket ships and orbiting satellites and stuff like this. Okay. So in this first lecture, before we talk about bicycles and try to understand why it is that a bicycle can stay upright while we're riding on them, we need to talk a little bit about static stability. Right. So static stability refers to an object's ability to be in stable equilibrium when it's at rest. Now, we met that word, equilibrium, when we were thinking about the equilibrium rest length of a spring, right? So for instance, I took apart one of my pens, I found the spring, and I said, okay, when it's at rest, so there's no net force and no net torque acting on the spring, this spring has some equilibrium rest length, some length that it adopts when no net forces act on it, right? So equilibrium, mechanical equilibrium, really just means experiencing no net forces and no net torques. And to be in stable equilibrium means that if the object is nudged a little bit, if you push it a little bit, it experiences a restoring force or a restoring torque that brings it back to its stable equilibrium position. So springs have a static equilibrium position, which is their equilibrium rest length. So a spring at rest is statically stable because if you try to push it, it experiences a restoring force trying to bring it back to its original equilibrium rest length. Similarly, you can imagine, say, putting an egg inside of a cereal bowl or something. Right? So the egg will roll to the bottom of the bowl and it will stay there, and that egg will be positioned in a place of static stability. Because if I push the egg a little bit, pushing it uphill a little bit, if I let go, it will experience a restoring force due to gravity and the way the egg interacts with the bowl that it's sitting in, that will bring it back to its original position. Right? On the other hand, if I flipped the bowl upside down, maybe I could precariously balance the egg on top of the bowl, but it would be in a state of unstable equilibrium, right? Or a statically unstable state, you could also say, right? Maybe you precariously balance it on top of the bowl, but if you give it just a little push, rather than returning to its position, it will just roll away and probably break on the floor. Right? So for a lot of objects in the world around us, we have an intuitive sense of whether something is statically stable or if it's about to fall over, right? If I balance this pen on my hand, you better believe that is a dynamically unstable situation. And so even the slightest push, in this case the air from the fan below me, will knock it over. On the other hand, your car sitting on its four wheels, that's pretty statically stable. You give your car a little push to tilt it a little bit, and it will just return to rest as soon as you let go. Okay, but what about more complicated things? Rather than relying on our intuition about how the world works, what physical principles that we've learned about can we use to determine if an object is statically stable or not? If we leave it alone, will it, blow over with the slightest little nudge, or is it in a state of static stability? Right? So one set of principles would be thinking about all of the forces and torques that act on that object. Right? So you can say, okay, I have some object. If I nudge it a little bit, I think about all the forces that are acting on it. I think about what accelerations that would cause. I think about all the torques that are acting on that object. I think about what rotations that would cause, what angular accelerations that would cause. And then I figure out, are those net forces and net torques pointing in the direction of back where I started from? Right? This is an effective way to answer the question of whether an object is statically stable or not, but it can sometimes be quite complicated, right? Because forces themselves can be quite complicated. So is there another way we can approach this? So how to tell if an object is statically stable? Question? One choice is to think about all net forces. Think about all net forces and net torques and ask, are they restoring? do the forces and torques point in the direction to bring me back where I started from before I was perturbed a little bit, before the object was nudged a little bit? More generally, though, another, sometimes even more powerful route is to think about the potential energy. Think about the potential energy. Okay. So let's take a specific example. Let's suppose I've got a block on a hinge. So I just have some hinge that I can rotate this block around, and the hinge doesn't let the corner of this block slide back and forth. And I imagine that I'm going to perturb this block. It's originally, sitting flat on the ground. And then I imagine perturbing it by lifting up one corner of it by some amount, right? So maybe I imagine there's like a tiny person, or maybe a full-size person, lifting up one corner of the block. And then we want to know if that person lets go, is the block going to return to lying flat on the ground, or is it going to flip over, right? So intuitively, we can kind of imagine this. We imagine we're rotating the block, and at first we tilt it just a little bit. That raises up the center of gravity of this block. The force of gravity is trying to pull that center of gravity down as low as it can. And so if we tilt it a little bit, the block will fall back down. If we tilt it enough, eventually, if we tilt it into something like this, just enlarging it for scale, eventually the force of gravity will point and make it rotate in the other direction, right? So there's a range of angles where the block will go back to where it started, and there's a range of angles where it will adopt a new position. Okay. Let's think about that in terms of the potential energy, the gravitational potential energy, as we lift that block up. Okay, as we lift that block up. So what I'm going to plot is, as a function of how much I tilt the block, what this angle theta is, what is the gravitational potential energy, right? So the gravitational potential energy will be related to how far up I've lifted the center of mass of this object by lifting up this corner, right? So I've got the potential energy as a function of this angle. And because I don't know the values of, what is the total mass of this block, and what are these side lengths, which maybe I'll just call the letter A, I'm just going to divide out by those so that I don't have to worry about them when I'm plotting. What would this function look like, right? So I have a function, the potential energy, due to this center of mass being lifted, from this height when the block is on the ground, or when the angle is 0. It gets to a maximum when the block is tilted like this. So that's like a 45-degree angle, or a pi over 4 in radians. That's where the center of mass is at the highest, and then the center of mass starts going back down again. It kind of traces out this shape. Okay, so if I draw the gravitational potential energy, that will look like this. It'll be a symmetric curve, which I'm quite bad at drawing, but it'll be something like this, where this point, the highest level of the gravitational potential energy, is when I've rotated this block pi over 4. Okay, pi over 4. So it turns out that the way this system will behave is that if I let go at any point, like let's say I lift it up this much, to this angle, the block will try to move in such a way to reduce its potential energy as fast as possible. And so if I'm on this side of this kind of hill of potential energy, that means the block will move this way. And moving this way, down the hill of potential energy, means reducing the angle. So I lift it up by some small angle, I let go, the block goes back to 0 angle. If I lift it up all the way over here, reducing the potential energy as fast as possible means the block won't try to go back this way. It will instead go down in this direction. And going down in that direction means falling over this way. And in fact, this is a very general principle. An object will feel a force in whatever direction reduces its total potential energy the most. So that is so important that I'm going to write it down. An object will feel a force, experience a force, in whatever direction reduces its potential energy, its total potential energy. The most. Okay, now in this case, where I'm just lifting a block, the only potential energy in the problem is the potential energy due to gravity. But suppose I additionally attached a spring to this side of the block, and I attach the other end of that spring to the ground. Well, as I tilt the block, that spring will stretch or compress away from its equilibrium rest length, depending on how the distance between, this point that I'm connecting it to and this point on the ground that I'm connecting it to, how much that compression distorts the spring. So instead of just gravitational potential energy, I would have gravitational potential energy plus the elastic energy of the spring, and the net force the object would feel would point in whatever direction reduces that total potential energy, the sum of the gravity and the spring in this case, energy the most. Okay, and often thinking about all of the energies in a problem can sometimes be simpler than thinking about in detail all of the forces acting on a problem. And so this is a very useful principle to think about, is an object in stable equilibrium or not? We can say, if we nudge the object, does that increase its potential energy? If so, it will experience a restoring force that tries to lower the potential energy again. So if I have a block that's sitting right here, any nudge in this direction raises the potential energy, and so the block feels a force going back to where it started. Okay. For the stability of objects, that only depends on gravity. So, am I in stable equilibrium or a statically stable position, just thinking about gravity, if gravity is the only force in the problem, this general principle leads to a very handy rule of thumb. I'm quite bad at drawing, so this might be a little bit of a challenge. But the idea is, suppose I think about, let's say, side view and top view of two things. Side view and top view of the same thing, rather. So I'm going to think about my canonical car. There's a wheel and another wheel in perspective or something. There's four wheels, and let's say this car is just sitting still on the ground. If I look at this from the top, so I've got, right now I'm just going to draw the ground, and I've got the 4 points where the wheels are contacting the ground. So wheel, let's say wheel dash ground contact point. All 4 of these things. Okay, so let's say we have all of these contact points, and let's draw the shape, the polygon, formed by connecting all of these points. Okay. This polygon, we're going to call the base of support. Okay, and the rule of thumb is that if you find the center of mass of this object, so again, I've got like a car in perspective or something, and the center of mass, is kind of sitting right over here. So let me say center of gravity, here's the center of gravity viewed from the top. Its location as viewed from the top. If you take a vertical line, going straight through the center of gravity in the direction that gravity is pointing, so from the center of gravity through to the center of the Earth, does that vertical line pass inside this base of support? If it passes inside that base of support, the object will be statically stable. And the reason for that rule of thumb is just geometry. If that condition is satisfied, then if you tilt the object up, the force of gravity will act in such a way to restore the object back down to where it was starting. So this is a rule of thumb for like rotational static stability. Is an object going to topple over or not? On the other hand, if this car starts leaning off the ground, so that the base of support looks like this, well, it's still statically stable. But if you get to the point where the vertical line through the center of mass straight down passes outside the base of support, then the object will be unstable and your car will tip over. Okay. It'll be at the best case scenario, it'll be in a state of unstable equilibrium, and it will be susceptible to even the slightest push. Great. But this rule of thumb, again, just to reiterate, is kind of just a feature of geometry that ultimately stems from the fact that if this condition about the base of support and the vertical line going through an object's center of gravity, if that vertical line pierces the base of support, then something is stable. That just comes from the geometric fact that if you take your base of support and that condition is satisfied, then if you try to rotate the object, you're going to raise up the center of mass of the object. And that means you will increase its potential energy. Ultimately, it comes from this idea that if any nudge you do increases the potential energy of the object, because objects feel a force in the direction that reduces the potential energy the most, if you do something that will always increase the potential energy, it'll feel a net force or net torque pointing it back to where it started.